All right, this video is based on integration by trigonometric substitution. What effectively is going to be going on here is that we're going to take algebraic forms of integrals, and because they don't have a means of solutions such as substitution, regular substitution, we're going to use a technique called trig substitution, which will convert, using right triangles, we'll convert the algebraic functions, and we'll set up right triangles, and then we'll convert the algebraic integral to a trig integral, and then we'll integrate it as a trig integral, and then convert it back to algebraic at the end. So let's jump right in there and see what we got. So over here we have our right triangle. There's the angle right there. The three sides, the opposite, the adjacent, and my favorite, the hypotenuse. Very important. So let's see. Now you look at some of these integrals, they would be pretty close. Like say, for example, this first integral, if it had an x in front of that radical, regular u substitution would work. This middle integral, if you had either just x on top by itself, that would be substitution. Or if you left it as x cubed and that was x fourth, regular substitution would work. Over here, if you just had an x on top instead of an x squared, you could use regular substitution. So for this technique, you're mostly looking at radical expressions or fractional powers, but not always. That example on the far right there, that shows you, this technique can also apply to integer powers like square. I'll talk about how to deal with that. Now, it's very important that we build our right triangular correctly according to the Pythagorean Theorem. Because if your triangle violates Pythagorean Theorem, anything you do after that's a complete waste of time because it'll be wrong. And also, every triangle has two and only two correct forms. So this first one I need to represent x squared plus 9 on a right triangle. Whenever it's plus between the two, it'll have to be the hypotenuse where that radical will go. One side will be the square root of x squared, which is x, and the other side will be the square root of 3, which is 9. Now, when I said there were two possibilities here, you could reverse the x and the 3. You can always reverse the opposite and the adjacent, and you would still have a valid triangle. So that's why it's there's always two ways to do it. So I could switch the 3 and the x. It just maybe affects what trig functions you're integrating. If you started out doing this and you were going to end up with cosecant and cotangent or something, and you didn't want to mess with that, you could switch them around. That'd be fine. But what I would recommend too is that before you go one step further, put what you think it is, and then check your Pythagorean theorem. A squared plus b squared equals c squared. Make sure that's right. Like I said, if that's not right, everything after that is wrong. Now let's look at this one. I have a square root of 7 minus x squared. When you have a minus, you can put it on either one of the short sides. I call the opposite and the adjacent the short sides. I could switch these two. Now that means so wherever you put it, no matter which side you put it on, the hypotenuse will be the square root of the first term. So it'll be the square root of 7, and the other side will be the square root of x squared, which is x. You can check and verify, but I guarantee you that triangle does represent a valid right triangle. The last one. Now, even though we don't have a radical here in the integral, that's okay. You still have to put, this is plus, so you put it on the hypotenuse. Now, even though there's not a radical, what you'll see is that to get to that squared, we'll raise that square root to the appropriate power. So that's a plus. Square root of x squared is x. I'll put that over here. Square root of 4 is 2. I'll put that in the adjacent. Now we're just looking at representing these. So let's see what this, as far as converting to trig. How do we do this? Excellent question. Now, one thing to keep in mind is we have to represent every term here, and that includes dx. So that's going to be very important. So we're going to always need to represent x from our triangle as a statement, even if x isn't in the intervals. Like the first one, x isn't there. Now the next two, we have an x cubed and an x squared. So there's two reasons we need x. But you always need x to get to dx because the derivative of x is dx. So I need this radical, and I want to combine the radical with the number. That's the simplest way to do this. The book shows different ways where it says, well, if this is this form, use this substitution. Well, that's fine. If you want to learn it that way, that's all right. I don't teach it that way. I'd rather it be more sort of a kind of intuitive, sort of memorizing a technique. I would rather sort of develop it this way. So if I put the radical over 3, that means secant of theta equals the square root over 3. So if you move the 3 over, that means the square root of x squared plus 9 is the same thing as 3 times secant theta. Now we need x. So we want to work with x and the number. In this case, tan of theta would equal x over 3. And then, so x would be 3 times tan theta. Now from x, we need dx. Just take the derivative of that. So 3 derivative of 3 tan theta will be 3 sec squared theta d theta. So everything's covered. Now, of course, we'll, take this further by putting this in an integral. This first one ends up being secant cubed, which is that one that's kind of complicated from integration by parts, which is not one that I would put on an exam. But you'll see how these. So we'll be converting these and integrating the trig function. But right now, we're just getting the setup idea down on this. All right, I need the radical represented with the number, combined with the number. So for this particular middle one here, cosine would work, adjacent over hypotenuse. So it's the square root of 7 minus x squared over square root of 7. Bring the square root of 7 over. So that means square root of 7 cosine theta will equal that radical term. Now I want to represent x with the number. So sine of theta will equal x over the square root of 7. Bring the square root of 7 over. So we have x equals square root of 7 sine theta. Take the derivative of that. So it's square root of 7 cos theta d theta. Let's come over to this next one. I want to represent the radical with 2. So secant theta equals square root of 4 plus x squared over 2. So 2 secant theta equals that radical. Now notice our first two integrals just had the square root only in there. Now we're going to see problems later that have like to the 3/2 power, maybe 5/2 power. This one's squared. So what you have to figure out is, okay, if I have the square root of something, what power do I need to raise it to make it become squared? Well, that would be the 4th power. Because I'll kind of write sort of a cryptic looking thing here, but x to the 1/2 all raised to the 4th. So that would be x squared. So that's how I knew to raise it to the 4th power, because I want to make it convert to x squared. If you obviously pick the wrong exponent, you can certainly change that. If you make a mistake, it's easily fixed. So you see I raised to the 4th power, and there you go. That gives me the 4 plus x squared squared. So the triangle can only have square roots. Any other power, you'll raise your trig function to that power. I'll see people make that mistake, especially when you see the 3/2 power we do here in a little bit. I'll see people put 3/2, something to the 3/2 on the triangle. That is not correct. You cannot put 3/2 on the triangle, only square roots. So I raise both these to the 4th power, and that takes care of your radical. And then now I need x for 2 reasons. Obviously, I always need it for dx, but I also need it for x squared. And so x will equal 2 tan theta, because tan of theta equals 2 over x. Looks like I skipped a step there. That's all right. Tan of theta is x over 2. 2 tan theta equals x. Therefore, 2 sec squared theta d theta would be dx. All right, now I know you're probably excited, ready to put these back in there and start integrating. So let's take a look at that right now, because that's what we'll do. That's what you would do. But this is the first step on how to get it set up. Now I'm starting with the one we just did right here. So I mentioned about always finding x to get dx. So I just copied that same triangle. So we're integrating that same problem on the right. So I have to replace x squared with 2 tan theta squared. Now the dx is right here. 2 sec squared theta d theta. That's your dx. And then on the bottom we have 2 sec theta to the 4th. Now I'm not going to spend a lot of time explaining the numbers part. You should be able to figure that out. Use calculator, do whatever. But anyway, essentially you have 3 2's on top, 4 2's on bottom, so it would leave a 2 on the bottom. You don't have to do that. I'm not saying you have to do that in your head, but just expand the numbers out and reduce it. And okay, that's pretty trivial math now, but let's focus on the trig. So you may not see me show a lot of work on those numbers things there, but I'm confident that you can be able to figure that out. All right. So you see we have a sec squared on top and a sec squared on bottom. A sec fourth on bottom, excuse me. So that would reduce and leave a sec squared on bottom, because the 2 on top would cancel with the 2 on the bottom. You have tan squared on top. So what we have here is tan squared over sec squared. Now you certainly, you could look at that list of stuff that I give you for test purposes from the section on trig integrals, what to do when you have tangent this and secant that. But what you're going to end up for this one is going to be converting to sines and cosines. So you can look at all that, but this is where you'll end up. That's kind of ironic if you flip these around. If you had a sec squared on top and a tan squared on bottom, you could actually let u be tangent and you would just have u substitution, because that would give you your sec squared on top. But one thing to keep in mind with integration, you can't have du on the bottom. I mean, it would make no sense to have, let me bring up a scratch page here. I mean, that's just good, this, you can't integrate this. That's like, what? But yeah, so no, well, I can just put du on bottom. No, you can't. The u can be on bottom, because obviously if it's du over u squared, that's equivalent to just being u to the negative 2. So don't make basic integration mistakes like that. So here we go. We convert tan squared to sine squared over cos squared. Sec squared is 1 over cos squared, so if you flip it over and multiply, what happens is the cosine squares will cancel, and you're left with just sine squared. Well, going back to the rules for sine and cosine, we've got a way to handle even powers of sine and cosine. And I have it copied right up here. We'll use the identity for sine squared, which will be 1 minus cosine of, this case, theta, 2 theta over 2. Now keep in mind, that's not the integral, that's just the identity. We still have to integrate it. So what I did here basically is just took that 2, tossed it out with that 2 right there to get 1/4. So we have 1 minus cos of 2 theta. Let's see, so antiderivative of 1 would be theta. And the antiderivative of cosine of 2 theta would be 1/2 sine of 2 theta. Keep in mind there would be a u substitution du, but if you just kind of know that, that will really save you a lot of time if you go ahead and just know that. Don't think a derivative, antiderivative makes it 1/2. The derivative would make it a 2. It would also be positive sign, but still. So yeah, I just kind of skipped that step. And now so we got to figure out a way to deal with this business right here, because the idea now is we've integrated it in terms of theta, we've got to get it back in terms of x. Because the final answer needs to finish in terms of x. Alrighty, so here's how you handle this. Theta. When you have theta, that means that part of the answer is going to be an inverse trig function. Because this is angle theta, meaning we can't solve for angle theta from here. We can solve for different trig functions of theta, like sine of theta, cos of theta, something. But this goes back to the idea of how inverse trig functions work. Now technically, you could pick any one of the 6 trig functions. So theoretically, there are 6 possible answers. But if this is a multiple choice question, you can kind of tell by the answer choices which one they're using. And generally, the one they use obviously would be kind of the more simplistic looking one. So in this case, they probably wouldn't include the radical. So in fact, that's even what Maple did too. So if tan of theta equals x over 2, by definition of inverse functions, that means that theta would be just tan inverse or arctan, obviously, same notation there, same thing. Tan inverse arctan of x over 2. So there's how you get theta. So there's this part of the answer, and I just rewrote, I don't know why I wrote arctan, but I always tell students those can be used interchangeably. So if it's sort of handwritten test, you could do it either way. Obviously, it's multiple choice, you can pick the right answer. So there's how you handle theta. It'll be an inverse trig function. Now, let's look at this sine of 2 theta. That's a different situation also. We have our triangles based on angle theta, so we can't get double angles based on that triangle without using an identity. And this is on your trig sheet. It's also, I believe, on this, might be on the calculus sheet too, the formula sheet, but it's definitely on a trig sheet. So you will need to use this identity. So now anytime you see this, you'll know to do this. Sine of theta equals 2 sine theta cos theta. So it breaks it up into individual angles of theta, and that's exactly what we want. All right, so what's going to happen here? So I'll put this in here. The 1/2 will happen to kill the 2. Now I left this 1/4 factored to the outside. Now, and I did in the final answer. Of course, if you're picking a multiple choice answer, you may need to distribute that 1/4, but that's all right. But this, you can do that if you need to. I mean, that's the least of your concerns. The main thing is getting to that final step, and then you can worry about whether or not you have to distribute. So we already taken care of the theta. Now that we have sine of theta and cos of theta, we're in business. We get those right off the triangle. So sine of theta will be opposite over hypotenuse. So it'll be x over the square root of 4 plus x squared. And then the cosine will be the adjacent 2 over the square root of 4 plus x squared. Now the Maple answer over here, which is correct, you can zoom in on that if you need to. But now, of course, they combine these, which you would have to do on a multiple choice answer. But if you multiply those 2 radicals together, you get 4 plus x squared. But my answer is equivalent to that answer, so it is correct. So there's the first exercise. So obviously different. Let's look at more. That's a basic idea, but obviously we want to look at a variety of, not necessarily going to cover all the basics here, but obviously that doesn't cover any possible problem you could see. Although I certainly don't make my exam problems, extremely rude or overly difficult, as far as how many steps you have to do, that sort of thing. Some of these examples probably more difficult than the test problems, although that was a good one. And this is a good one too. I like this one. So this one actually is the middle example up here. I mentioned before, I'm not going to do that first one as an integral. I thought it was good to set up, but it's because it was secant cubed, and there's no way I'm going to ask that on a test. But, if you felt like you wanted to have some fun and try that out and use the integration by parts method for secant cube and see if you could do it for your own benefit. You wouldn't have to for a test, but I certainly wouldn't try to stop you from doing that, but I think I would make sure I practice, these more standard problems first. So I copied the triangle back down here, and there's all this information. So if we square root of 7 sine theta is x. So then if it's x cubed, we have, see there I have the cube there. And then there's dx is square root of 7 cos theta d theta. Then on the bottom, the square root of 7 minus x squared is defined also as the square root of 7 cosine theta. So you can see I cancel those two terms, write out both the radical and everything are gone. So all we have is the first part. And once again, the number simplification you should be able to do. But 3 square root of 7s multiplied together is going to give, because every 2 square root of 7s makes a 7. So it'll give you 7 square root of 7. Sine cubed. All right, to integrate sine cubed, we have to use a technique from the trig integral section, how to integrate when sine is odd and positive. So what we do is we basically split this up into sine squared times sine, which we're saving for du. And then this sine squared we convert to 1 minus cos squared. So it's going to split it up into two different integrals. Now we have to watch out here because u is going to be cosine, therefore the du will be negative sine. And so we have to adjust for a negative. You may have to distribute it at the end. But what I did is I went ahead and just moved this negative outside, because that way out here it will apply to both these terms. Another way you could have done it was that's the way I did it, but I will mention that you could have left this positive and you could have applied the negative here and reversed it and made it u squared minus 1. That would have worked. See, there's the 1 minus u squared coming from here. Could have done that, but either way it would all multiply out to be the same answer in the end. So like I said, there's different ways you can handle that negative. So you take the antiderivative here. Antiderivative of 1, of course, would be u. U squared would be 1/3 u cubed. So now we have to make, actually you have to make two substitutions here, and this for these kind of problems. You have to go from the u to trig, and then from trig to algebraic. Not that difficult, but so u is cosine, so I put cosine right there. 1/3 cosine cubed. So we go to the triangle, or we also have it written right here for cosine, but cosine is the square root of 7 minus x squared over square root of 7 minus 1/3 square root of 7 minus x squared over the square root of 7 cubed. Now, in Maple, what I did is I took my answer and instead of trying to convert my answer to their answer right there, I took the derivative of my answer and then simplified it and got the original problem. So all that means is my answer is one correct way to write it. But the negative, like I said, these could change the signs if you distribute the negative. There's more than one correct way to write this. I'm not big on trying to get too complicated on the factoring of the answers or anything like that. I prefer kind of leaving it sort of in a form like this. Let's jump down to this next one. So let's see what we have here. We have dx over x squared times the square root of 4x squared minus 9. So I need to build me a triangle that has the square root of 4x squared minus 9 on it. Since we have a minus between those two terms on the radical, that means it must go on either the opposite or the adjacent side. So take your pick. Doesn't matter. Only when it goes on the hypotenuse is when it's plus. So I chose the opposite side. So in that case then, so whichever side I chose, the hypotenuse was going to be the square root of this first term. The square root of 4x squared is 2x. Square root of 9, of course, is 3. And as I said earlier, you might want to check Pythagorean Theorem just to be safe. I can tell that this one's right, but obviously for your benefit, wouldn't hurt to do a quick a squared plus b squared equals c squared. So now let's build everything we need. We need x to get dx, but we also need x for x squared, and we need the radical, of course. So I'm going to work with the radical and the number. Always do that first. Well, it doesn't be first, but I mean compare the radical with the number. So tangent would be the radical over 3. So 3 tan theta then equals that square root of 4x squared minus 9. So that takes care of that term in terms of trig. So now I'm going to work with the x and the 3. So secant of theta equals 2x over 3. That means 3/2 sec theta is x. Therefore, the derivative of secant is secant tangent. So it'll be dx will be 3/2 sec theta tan theta d theta. So now we have to go to our triangle, convert everything over from trig, from algebraic to trig. Everything must go. You can't just change some of it and leave a random x sitting there. You cannot do that. Everything must be represented as trig. In other words, including the dx, which we always convert to d theta. So let's see what we have. So there's our dx in the numerator. That's the only thing we have in the numerator. X squared on the bottom would be 3/2 secant theta squared. And then I have the radical, which is 3 tan theta. So you see right off the bat, I cancel the tan of thetas. I'm not going to go through all the number business, but you have 3/2 over 3/2 squared times 3. Play around with that. It'll turn into 2 over 9. Like I said, you're not supposed to immediately look at that and know that. That's my point. But I don't want to spend time going through the trivial part of the numbers. I want to focus on the trig function. So we have a secant on top and a sec squared on bottom. That leaves a secant on bottom. Now, here's a very important rule here. Should have put this. Let's see if I said that. Well, I'll say it verbally here. This would have been a good time to put a little Stewie thing in there, but when you're integrating trig functions, you never integrate a constant over a trig function. Like you never integrate 1 over sine, 1 over cosine, in this case 1 over secant. You always need to convert it to its reciprocal trig function. A lot of times students would take a problem like this where it says 1 over sec theta, and they would call that natural log of secant, and that is not correct. That also applies to if it's higher powers. Even if it was 1 over sec squared, you would still bring it up and make it cosine squared. So here, this looks like it could be complicated, but actually turns out it makes the problem quite easy. Well, not, I mean, we had to do it. It's not like we couldn't have done it without doing this, but secant on the bottom, 1 over secant, is the same thing as cosine. So the only thing we're left with now is to integrate cosine. So the antiderivative of cosine will be sine, so we have 2/9 sine of theta. So our answer is just going to be, and we go to the triangle to get sine. See, we don't already have sine here, so we have to get it. Opposite over hypotenuse. So sine is the square root of 4x squared minus 9 over 2x. So we have 2/9 there, and there's that part, plus c, and that's it. This answer, I just canceled the 2's. You know, it's not like that. Obviously not wrong if you don't, but. And Maple seems to like my answer, so that's good. Yeah, they have the simplified answer there, so that's terrific. All right, let's come down here and take a look at this one. I'm a 5/2. Here's another one of 3/2. 5/2. All right, I never let these get too out of hand, you know, for test purposes. This isn't too bad. A little messy. Okie doke. So you see there's not much variable stuff. There's have a 2 on top, and we have 25 minus x squared to the 5/2 in the denominator. And I mentioned earlier, but I'll mention again, is you cannot put 25 minus x squared to the 5/2 power on your triangle. That is not what we do. The only thing that can go on a triangle is a square root. Then when we convert it to trig functions, then we can raise it to the appropriate power we need to get it to 5/2. So always remember, so look, I put the square root. Now it's a minus, so I could have chosen either one of these two short sides here, opposite or adjacent. I chose adjacent this time. But I could have flipped that in the x and I would have been correct. But the hypotenuse is the one that has to be the right thing for sure. You can't, there's only one thing the hypotenuse can ever be in every problem. But the opposite and the adjacent could switch. So choosing the adjacent, that means the square root of 25, 5 will be the hypotenuse. Square root of x squared is x will be the opposite. So let's build us the trig functions based on that triangle. So we need x to get dx. So sine of theta is x over 5, x equals 5 sine theta. Therefore, dx will be 5 cos theta d theta, so that takes care of the dx. Now, so we're going to get that radical. Cosine of theta is the radical over 5, so 5 cosine theta equals this radical term. Okay, so here's where we're going to deal with that 5/2 power right there. To get something to go from 1/2 to 5/2, you raise it to the 5th power. That's how we take care of the 5/2. So you see, that's what I did right here. I raised it to the 5th. So 5 cos theta here to the 5th will equal the radical of the 5th, which will produce the 5/2 power, not the triangle itself. This step over here is how you get it to whatever power you need it to be. And that ends up being 5 to the 5th is 31/25 cos 5. So let's build us a trig integration here. So the 2 is just the 2 right there. Dx is 5 cos theta d theta. And then on the bottom we have 31/25 cos to the 5th. And you get 5 over 31/25 reduces to 6/25. So we have 1 cos on top, 5 coses on bottom, so that leaves 4 coses on bottom. And just like I said in the last problem, we never integrate a number over a trig function to any power, so it must be brought up to its reciprocal trig function. So 1 over cosine to the 4th will be secant to the 4th. And if you look at the rules from the trig integration section, there is method for handling secant even and positive. You take the sec 4th and you save a sec squared for the du. You split it up to sec squared, and you convert the first sec squared to 1 plus tan squared. And we have, all right, so let's see. 1 plus tan squared, and we have sec squared. There's the constant on the outside. So that just becomes, we don't have to split this up in two integrals. We can just write it like this, 1 plus u squared du. And there's no adjustments here. We had one earlier where we had to adjust for the negative. But that's not the case here because the derivative of tangent is positive sec squared. So there's no adjustment here. So all right. Now, no, so it's perfect fit, 1 plus u squared, so take the antiderivative, which antiderivative 1 will be u squared will be 1/3 u cubed. Put tangent back in there, so we have tangent plus 1/3 tangent cubed, and now we get tangent from the triangle. Tangent is opposite over adjacent, so it's x over the square root of 25 minus x squared. So we replace that right here, x over the square root of 25 minus x squared, and then 1/3 of that term cubed will be the next part. Terrific. And of course, you could play around with that answer, you know, 1 and 2, but don't think you'll necessarily need to. So here's one. What do we have here? Back to having a plus here. So we have square root of 25x squared plus 4 over x to the fourth. So now we have a plus for our radical. So it's going to go on the hypotenuse. So one side has to be the square root of 25x squared, which is 5x. The other side has to be the square root of 4, which is 2. And then let's go from there. So tan of theta will equal 5x over 2. Therefore, x will be 2/5 tan of theta. Derivative of that will be 2/5 sec squared theta d theta. And so now let's get the radical involved with the 2. So secant would be the radical over 2. So therefore, 2 sec theta will be the square root of 25x squared plus 4. Let's put everything back in here. All right, square root of 25x squared plus 4 right here is 2 sec theta. And then dx right here is 2/5 sec squared theta d theta. And then on the bottom we have x to the fourth, which will be 2/5 tan of theta all raised to the fourth. And you play around with the numbers, you'll get 125 over 4. One thing you can do is the 2/5, we'll take out one of the 2/5 on bottom. So basically you have 2 divided by 2 over 5 cubed. I mean, okay, I'll just put this just for grins here. I'll actually do this one. Take 2 divided by 2. If you want to do it this way, that's fine. I want cubed. Then I can do a math frac. 125 over 4. Yeah, so that's why I'm not spending much time on the simplification of the numbers. But yeah, use a calculator, that's fine. So what do we have here on top? We have secant cubed over tan fourth. And that's going to fall under the guidelines for converting to sine and cosine. So we have 1 over cos cubed, and we have sine fourth over cos fourth. So flip them around, fraction, divide, invert, and multiply. So you flip it over, and obviously I didn't show that step, but obviously you'd want to write that step if you needed to, so you can see what lines up with what. And you'll end up with a cosine on top and a sine fourth on bottom. All right, that looks like, so then, your first instinct might be to go to the, the rules for sine and cosine. But actually, always look to see if you think basic substitution would work, before you do anything. It's always a good idea. That's what's going to happen here. Because remember, your du's got to end up in the numerator. So if you look at this, actually u just equals sine of theta, and du would be cosine of theta. So you have a perfect fit right there. And of course, then you need to bring that up. You can at some point. But see, so that's, I did it right over here. So you didn't have to bring the sine up. You could just say du over u to the fourth. I sort of skipped that step, but then rewrote it then right here correctly as u to the negative fourth. So that's all you end up with is u to the negative fourth. Of course, we have our constant in front there. So all we have to do here is a power rule. So it's u to the negative 3 over negative 3. Combine those numbers together, you get negative 125 over 12. And u to the negative 3, so you have to change this back into, so u is sine. So essentially this becomes sine of theta raised to the negative 3. So sine will be opposite over adjacent. So it's 5x over the radical. So it's 5x over the radical raised to the negative 3. Now let me kind of point something out here to you, especially if it's a multiple choice type question. A handwritten question, I have no problem leaving it like that with a -3. That's no issue at all. But on a multiple choice question, they probably would have it as a positive exponent, which means all you would have to do is flip this fraction over, flip it upside down, and make that a +3. Now, Maple went a little bit further with the simplification, but you see how the radical now is up on, they got that 5 cubed out, basically, and it cancels out with the 125, so that's all that happened. But yeah, so Maple flipped it over and just, okay, so the square root cubed is +3/2, and then that x to the -3 will be x to the 3 on bottom, so you probably would have to flip that around to make that exponent positive. But other than that, not too bad. Okay, here's one with the 3/2. So the x squared plus 3 will have to be the square root of that. Will have to be the hypotenuse because it's plus. And we've seen this kind of problem earlier with that first page of examples I did with the 7. I did that on purpose. So I didn't say this earlier, but I'll go ahead and say it now. So, but you've already seen this. Is that this, when you have the x squared plus or x squared minus, that does not have to be a perfect square of an integer, in other words. So, a lot of problems you'd probably be looking for it to be like 4, 9, 16, 25, but that's okay. If this is a 3, that just means that side would be just the square root of 3, so that's okay. There's just so many examples will show them as perfect squares, you might think it always has to be that way, but it absolutely does not. So we have I put square root of x squared is x. I chose the opposite side, square root of 3 for the adjacent, but theoretically, those two could flip, not the hypotenuse. Check Pythagorean Theorem to be on the safe side, but this triangle is okay. And let's get everything represented that we need. Tan of theta is x over the square root of 3, so square root of 3 tan of theta equals x. Square root of 3 sec squared theta is d theta. Equals dx. And let's see what we needed here. So we come over here, dx, we just got that right there, so there it is. And then to go from the square root to the 3/2 power, you cube both sides. I guess I could have put a cube right here to show you, but yeah. But basically both sides are being raised to the 3rd power. We had a 5/2 a minute ago where we raised it to the 5th. But like I said, I've seen people, like I said, looking at handwritten tests where they put 3/2 on the triangle, but that is not right. So we have square root of 3 secant cubed on the bottom here. So let's see, play around with the numbers there. You basically have 1 square root of 3 on top, 3 square root of 3s on bottom, so it's going to leave 2 square root of 3s left, makes a 3, 1/3. And then we have secant squared over secant cubed, leaves a secant on bottom, which we've already talked about, so you can't integrate this way. So you bring the secant up, make it cosine. So this one's actually pretty easy. Antiderivative cosine of sine. And then there you go. So you go to the triangle. Sine's going to be opposite over hypotenuse. So it's 1/3 x divided by the square root of x squared plus 3. All right, that one wasn't too bad. Let's see what we have here. I'll look ahead and see. All right, let's take a look at this one. This is fine here. This is actually, let me look at, okay. I thought it was going to be exactly the same as the one on the right. It's similar, but not exactly the same. I was going to skip it in that case, but you see that numerator here has an x squared. Ours is a constant. So I thought, okay. So it's at least different enough to take a look at. I didn't want to do the exact same basic problem twice. Alrighty, so square root of x squared plus 25, that must be the hypotenuse. Square root of x squared is x for one side. Square root of 25 is 5 for the other. So tan of theta is x over 5. And let's see, I'm going to check something for a second here. All right. Does end up very similar looking to that other example, but so 5 tan theta equals x, therefore 5 sec squared d theta is dx. Secant will be the radical over 5, so 5 times secant is the square root of x squared plus 25. So there's the 2 I just took to the outside. 5 sec squared d theta represents dx. And then we raise, I didn't show, there it is right there, the fourth power. So to get from square root to fourth to squared, to get from square root to square, we raise it to the fourth. So we've already seen that before. So I have 5 sec theta to the fourth. So basically I have 1 5 on top, 4 5s on bottom, which leaves that as 125. And then sec squared on top, sec fourth on bottom. That leaves sec squared on bottom. And which brings it up as co-squared. So the only difference between this one and we did earlier was sine squared. But the identities are similar. Now this one, so sine squared is 1 minus, this one plus. So the identity is 1 plus cosine of 2 theta over 2. So I cancel the 2's. Antiderivative of theta, 1 is theta. Antiderivative of cos of 2 theta is 1/2 sine of 2 theta. And then we saw earlier that theta must be represented as one of the trig functions. Inverse trig functions, excuse me. Usually written in the simplest one. This one happens to be tangent, would be the arctan would be the simplest way to go. Because if tan theta equals x over 5, that makes it real easy to say arctan of theta equals arctan of x over 5. Even though mathematically there are 6 possible answers there, but that would be the simplest one. So we have sine times cosine right here. So there you go. Sine is x over the radical. Cosine is 5 over the radical. Multiply those together. It's possible you might have to combine those two radicals together into x squared plus 25 as a single denominator. So it would be 5x over x squared plus 25. And then our beloved plus c at the end. Okay, let's take a look at this one. Square root of x to the fifth over the square root of 25 minus x squared. Now I have to admit it's probably a little too lengthy to put on an exam, but I would kind of watch how I do it anyway. It's got a good technique from trig integration that we would want to know how to do. The trig integration part of this is it's relevant from a testing standpoint, but the whole thing might be just borderline a little too messy. But doesn't mean it's super hard, just a little messy. Would make it hard to get a multiple choice answer right. So I have to take that into consideration. With that being said, it's still a fun problem. I like it. So I built my triangle because I have a minus on the short side. And then square root of x squared will be x, and the hypotenuse has to be the square root of 25, which will be 5. So sine of theta is x over 5. X equals 5 sine theta. 5 cos theta d theta equals dx. Cos of theta equals the square root of 25 minus x squared over 5. 5 cos theta equals the square root of 25 minus x squared. All right. So there we go. And let's put everything together. And x to the fifth right here will be 5 sine theta to the fifth. Dx is 5 cos theta d theta. And then the radical is 5 cos theta. So you see these 5 cos thetas will cancel out directly. And That leaves, so 5 to the 5th is 31/25. We have sine to the 5th. And that uses the technique for trig integration where sine is odd and positive. And it does satisfy my personal restrictions that I promise that you never have to do more than squaring a binomial on any of these problems. Like I would never give you a sine to the 11th and expect you to have to take 1 minus cosine squared to the 5th. I would not do that. But I did say square. So square was my maximum thing right here. So, and that's what applies in this problem. So we break it down into sine fourth and sine. So sine fourth is 1 minus cos squared squared. So you FOIL that out. Remember, you can't just square the individual two terms. FOIL it out. You'll get 1 minus 2 cos squared plus cos fourth. Sine theta, d theta stays with all that. And, and you see the u du with the negative? Okay, like I said, there's a couple different ways you can handle this. I chose to put the negative on the outside because that negative 31/25 does apply to all three terms. Or I could have left it positive and I could have changed the sign on all three. So either way, two correct ways to do it. I just left the negative 31/25 on the outside. So this becomes u minus 2u squared plus u to the fourth. Okay, I skipped a step here. Okay, I skipped that. That's okay. That 2u squared is the antiderivative would be 2/3 u cubed, and then the antiderivative of u to the fourth would be 1/5 u to the fifth, and of course the antiderivative of 1 du is u. So I kind of did that step and then put the trig function back in at the same time. I guess I wanted to make sure I stayed all on one page. So it's a little messy, but not that bad. So you put cosine back in there, and then you see, so you take cosine off. So off the triangle, cosine is the square root of 25 minus x squared over 5. And you replace that in there for each term. And you see, so it's minus 2/3, and we cube it here. And then radical over 5 to the 5th. And then so, yeah, that's the correct form of the answer. But I can't imagine how bad it would be simplified in a multiple choice format. So that's kind of one reason I don't want to use it. But as far as getting to that, it's not too bad. So, all right, looks like here's one I just kind of made up and kind of did the answer in Maple to see how we would, see what we were shooting for there. So just kind of a made up example. Let's see what this is all about. So it's x times the square root of 1 minus x to the fourth. Now, if that x in front of the radical had been x cubed, we would not have needed regular substitution would have worked. But since it's not, it's now time for trig substitution. All right. So let's see what we have. Got a minus, so that means my radical must go on one of the two shorter sides. So I'll put it on the adjacent. And that means the square root of, keep in mind the square root. I don't always like using 1 because you could actually get away with forgetting to take the square root and still get it right. But that 1 in the hypotenuse is technically the square root of that 1. Square root of x to the fourth is x squared. So let's see what we have. So cosine theta will be adjacent over hypotenuse. So cosine of theta will be the square root of 1 minus x to the fourth. Sine of theta will be x squared over 1. So sine of theta is x squared. Now this is a little bit different here. Different ways you can go about doing this. A little trickier, so maybe that's why I thought this was a little interesting. Usually I always said solve for x, in order to get dx. But what I did here is I just took the derivative of x squared and took the derivative, of course, of sine, got cosine theta, d theta. Now, if you take the derivative of x squared, you're going to get 2x dx. Then I looked at this and I noticed that, well, hey, my integral has an x and a dx, so I can incorporate. I know I haven't done that in any of my other examples, but that's something you can do. But I would be careful in a lot of other problems trying to do this. But you can keep the x and the dx actually as one combined term if it works out that way, like it did here. So I can just treat x dx as not two separate things multiplied together, one deal. So divide both sides by 2. So x and dx together in this one will represent 1/2 cos theta d theta. So what we have, I pulled the 1/2 out, so we have cos theta will represent the radical, or whatever order you do it in, but I just square root of 1 minus x to the 4th, and then just pretend like I moved the x at the end down there with the dx. And then the cos theta d theta comes from right here. So it's just two cosines multiplied together. So you end up with cosine squared. So we have to use the identity that 1 plus cos of 2 theta over 2. And 1/2 times 1/2 is 1/4. Antiderivative of 1 is theta. Antiderivative of cos of 2 theta is 1/2 sine of 2 theta. And then we've seen these problems before. Theta must be an inverse trig function. Here I just chose arc sine, but as I've said before, there's 6 possible answers. So if sine of theta is x squared, theta would equal arc sine of x squared. And Maple chose that way too. But my point being is you could also say that theta equals arc cosine of the square root of 1 minus x to the 4th. That would be correct also. So then you end up with using the identity for 2 sine 2 theta, 2 sine theta cos theta. So we already have sine and cosine right there. It's x squared and the square root of 1 minus x to the 4th. And then so I have a 1/4 to the outside there, and I have arc sine x squared plus x squared times the square root of 1 minus x to the 4th, which my answer matches Maple's answer if you distribute the 1/4 through there and reverse the terms, but we basically have it. All right, very good. I didn't give it a seal of approval here. Let's take a look at this next one. Now, it's kind of two of the same thing. I'm just going to look at this one real quick and not worry about that last one. But you can actually use trig substitution for certain types of integrals involving e. I thought that was kind of an interesting idea. So I basically have the square root of 64 minus e to the 2x times e to the x dx. So I'm going to put that radical on one of the two short sides. I chose the adjacent. That means the hypotenuse will be the square root of 64, which is 8. And now this is a little tricky, but the square root of e to the 2x is e to the x. And you can show that real easily. Remember, when you take a square root, you're raising something to a half power. It just looks a little bit weird with these e's, and it does, like, the square root of x to the 4th is easy to see that it's x squared, but it's because it's half the power. That's really what it really boils down to. So that equals e to the x. So that's, then, like I said, e to the x does satisfy the right triangle. So we're good here. And so the cosine of theta will equal a radical over 8. So 8 cosine of theta then is the same as the square root of 64 minus e to the 2x. And sine of theta will be e to the x over 8, which makes 8 sine theta equals e to the x. Now this one, a couple ways you can go about this one. I've done it the other way and got it right also. This way is much more efficient, though. It's much better, but the other way works too. Is you could take this part right here, and you could natural log both sides to kill the e, which would leave you the x, and then take the derivative of x to get your dx. That absolutely works. But this is much better because this is similar to what I did in the last problem. but it's not, it's e's this time though, is a little bit different because of that reason. But since the derivative of e to the x is e to the x dx, we can use that since we have that in our integral right there. Now, if we didn't have this e to the x here, then we would have to have done what I said. We would have had to have taken the log of it, solve for x just to get dx. But since we're actually looking for e to the x dx, let's take advantage of that. So I'm just going to differentiate this as is. So the derivative of 8 sine theta will be 8 cos theta d theta. So 8 cosine theta d theta will take care of both e to the x and dx together right here. Very similar to the last problem, except it's just e's now. And there's the 8 cos theta represents this first part. So you end up with cosine squared, so we just basically have done that. So let's kind of go through this pretty quickly. We just used the cosine squared example. So you have 1 plus cos 2 theta, antiderivative is theta plus 1/2 sine of 2 theta. And then of course you use the identity we need right here, which is 2 sine theta cos theta. 1/2 kills the 2 there every time. So theta, I'm using arc sine of e to the x over 8. Could have used, other options, but that was just as easy. So theta, right from right there, is arc sine of e to the x over 8. And we have sine, which is e to the x over 8 right here. And then we have cosine, which is square root of 64 minus e to the 2x over 8. So Maple wrote it a little bit differently, the e to the x squared, which is the same thing, of course. But so if you distribute the 32, and then my answer does match that. You have 32. We have 2 8s multiplied together on the bottom, so 32 divided by 64 makes the 1/2 for this part right here. And that one's just 32. So we have it. Let me scroll down this next one. Similar idea. Oh, this one I actually, I'll look at it real quick. You see it's pretty short, so I'll kind of skip the setup part here, but I will mention because it's a minus, it has to be on one of the two short sides. Now this one, because I didn't have a e to the x dx up in the numerator, so I did have to get x. So I did log both sides, and then x equals 1/2 log of secant. Therefore, the derivative, remember the derivative of natural log is du over u. So the derivative of secant is sec tan over sec 1/2. And we have dx equals 1/2 tan theta d theta. And let's see, all right. To put everything back in here, it actually works out pretty easily. You end up just integrating cosine, which is nice, because these cancel and you leave a secant on the bottom. So yeah, this one I had to solve for x to get dx, but the other one I did not, because I had an ex up there. So, well, that concludes this video on trig substitution.